we'll move through this presentation, and then after lunch, we'll continue on the discussion around reference systems and in particular, this component on the infrastructure. And I just wanted to take you through here a description of some of the elements of the global geodesy supply chain is what we refer to it as. And that is that it's made up of a complex technique of this infrastructure and the people and the resources that we were talking about before. The first step is these observatories, and that helps us understand the ongoing movement of the changing shape of the Earth over time. So a lot of people think the Earth is static and we only need to measure it once, but it's continually wobbling, it's continually moving. And if we're not monitoring how the Earth is moving, we can't collect that data, analyze it, and create things like geodetic products you see there in orange, which is not just the reference frame, but things called Earth orientation parameters. And that's really a fancy term to say, how is the Earth wobbling over time? You can think about the Earth like a spinning top. You know, the kids' toys, you spin it and it spins around on the table, and then after a little while, it starts to wobble a little bit. Those movements, those wobbles need to be recorded, because if the satellite doesn't know exactly where the Earth is at any given time, we can't use that satellite information accurately and reliably. So we need to know exactly where the satellites are, and we need to know exactly that position of the Earth at any given time. And this is where the astronomy community plays such an important role, because they can measure things that we can't using things like GPS. You can't measure the spin rate of the Earth with GPS. You need to use very long baseline interferometry. So the geodesy community is this combination of lots of different techniques that allow us to make these observations of the Earth, collect data, get it analyzed, create products, and then we feed that information into the satellites to make sure that they're working accurately and reliably. Here's an example of some of the ones that of these observatories that I mentioned. So very long baseline interferometry. It's critical for things like, as I said, Earth rotation, measuring the positions of stations on the ground, and quasar positions. Who's heard of quasars? Put your hand up if you've heard of a quasar. Jack, lucky you put your hand up. Yeah, Alette, thank you. All right, so a few. So quasars, they're cool, right? We struggle to get people interested in geodesy, but quasars are like supermassive black holes with gas jets coming out. And wonderful people like Alette and Jack, they can measure, they orientate their antenna to these positions of these quasars, and by measuring the quasars from different locations on the Earth, we can measure the difference in distance in place on the Earth to the millimeter level, and you can measure the spin rate of the Earth. It's incredible. We also have satellite laser ranging. We shoot lasers at satellites, yet we can't get kids to do geodesy. I don't understand. We're doing something wrong. It's some amazing technology we have. And so that laser ranging is used to not just monitor the orbits of the satellites, but as they collect that information about the satellites, they can help determine the center of the mass of the Earth. And that is the center of our reference frame. Again, another critical piece of information we need. We then have the global navigation satellite systems like GPS, GLONASS, Galileo, Beidou. They're all our positioning and navigation and timing satellites. That's how we access the reference frame and access this really high detailed information. And then there's DORIS, which is a French initiative, and it's almost like GPS in reverse. So you transmit from the ground and then it collects the information at satellites. These are all complementary space techniques that we use to determine the reference frame and also determine the Earth orientation parameters. I'm going to skip over this because we've got to finish on time. Gravity is the other key one. Being able to measure gravity, they talk about absolute gravity, which means the absolute pull from the center of the mass of the Earth, or relative gravity. These kind of measurements are critical for understanding the development of our height datums. And then there's the sea level information, leveling altimetry from satellites. You got satellite radar altimetry and tide gauge observations. All this information comes together to help us develop our height datums and geoid models. Here's an example of where the different techniques come together. So if you're looking to develop an international terrestrial reference frame, which is our reference frame for the Earth, here's the location of all these different techniques around the world. And you can see there's quite a significant bias to the Northern Hemisphere. And that's because it's not these, most of these locations of where the measurements are taken, it's not by design. It's normally by who has funding to do this kind of work. So if you compare that with what would be an ideal network for monitoring and measuring the Earth over time, this is not what you would come up with, but it's what we currently have. And part of our story is telling politicians that this is being developed in quite an ad hoc format, and we need to make it more reliable and more robust in the future in the way that we set up this network to make sure that we have good observations and redundant observations from all around the Earth. So I'll move through some of this, but they're all in the slide deck, so you can go back to it later on. For those of you who haven't seen what radio telescopes, these are the types of VLBI telescopes. That's what they look like. And you can see there we've got Wetzel, which is in Germany, La Plata, which is one from Argentina, where they do that in collaboration with Germany. And then the O'Higgins telescope with a couple of beautiful penguins down there sitting on a rock. So that's in Antarctica. And these are what the laser ranging systems look like. So you can see a dome is over the top, and that's to protect the technology. And they have different sort of openings that they use, that they can open it up and make observations. But they're all kind of different technology. And this is another thing that we're struggling with at the moment. It's some of the technology is not standardized. Like the way we do VLBI observations is not the same everywhere. And the way we do SLR observations is not the same everywhere. So it also means that if you have a problem at one particular site, sometimes there's not a spare sitting around. Or in the case of what we had in Western Australia, we had to buy pieces off eBay in order to keep some 1970s technology working. Other parts of it are stuck together with sticky tape and Band-Aids. We can't keep running critical infrastructure systems like this on sticky tape and eBay. We've got to be able to tell politicians that infrastructure like SLR, like VLBI, if we don't have a strong foundation network around the world, then it's going to impact on all the positioning and satellite applications that come after it. And GNSS, that's a great network if you look at it. This just shows that it's much easier to set up a GNSS station than it is a VLBI or an SLR system. And you can see that we have quite a good contribution from all around the world that provides us with a great network of international GNSS stations. And we'll be talking about these different services in a bit more detail. Ryan will be covering some of that later in the week, and we can learn more about them. And Doris, again, very similar to the IGS in that they have a good distribution spread out around the world. And again, this is because, in my opinion, it's because they have a great governance structure. And it's almost a simplified governance structure because Doris is run entirely by the French government and through the space industry in France. So they have a very clear message on why they run it. They are able to explain that message to decision makers, and then they get funding to operate a very strong network worldwide. And that's something that we would like to copy for SLR and VLBI as well. Who's seen a gravimeter like that one on the left before? That's called an FG5. Anyone seen one of those absolute gravimeters? We've got a few. Yeah, you have one at home? CG5. Okay, CG5. Right. Another absolute gravimeter. Yeah. So these are really good at being able to improve our global understanding of the geoid, which is that sort of oddly shaped potato that you can see there on the right-hand side, as my university lecturer used to call it. And it's critical to be able to collect these land-based information about gravity and changes over time, and the use of the terrestrial gravity on the ground. And the real benefits come when you link it with airborne and satellite gravimetry as well. And we'll talk a bit more about that later on. Here's an example of where they've all been brought together. So this is at Wetzel in Germany. One of my colleagues from Germany shared this with me. And you can see how what they're trying to do here, I call it a super site. they're called core sites, but I like to think of it as a super site when you're talking to a politician, because it's bringing together all the different techniques. It's bringing together the VLBI, the SLR, the gravity. They've also got a couple of different types of gravity here, as well as time synchronization, which is highly accurate clocks with GNSS. So the benefits of having this all in one site is, first of all, you get much easier for your lease agreements rather than having a land lease where you need access to multiple sites, but you can tie these techniques together. And this is one of the benefits of Geodesy, is because VLBI is really good at some things, SLR is good at other things, GNSS is good at some things, and gravity does something completely different. But the real benefit is when you can link these techniques together. So about every 18 months to 2 years, these local tie surveys are done with a total station to connect the center of all these points together. And then this tie information is used by people like Zahir El-Tamimi for the determination of the ITRF. They're bringing the techniques together to create an accurate reference frame using the best bits of all the different geodetic observations. And here's an example of the beautiful survey work that's been done at Wetzel. You can see the lines there that represent all the observations that get taken using the total station. So they're making horizontal measurements, but also they're doing leveling between these points. So a site like this, I would predict it takes probably about 2 weeks to do a local tie survey of that type, because it's so complex and there's so many different measurements that you need to take. And it's got to be done at that sub-millimeter level. So it's extremely impressive type of surveying. And then there's timing and frequency. And this is getting a lot of traction at the moment because everyone's thinking about quantum. Everyone loves to talk about quantum clocks. And if you think about quantum in particular, you can start to get to the point where you can use the difference in time, captured it by clocks at different heights, to actually tell you the height difference between 2 points. Because of the laws of relativity, you can actually detect time difference, which tells you a difference in height using clock information, it blows my mind just thinking about it. But it's happening now and people are doing studies on this, and it's going to be phenomenal to think about what we can use timing and frequency information for in years to come. It gives you a clearer description of where we have these multiple techniques. So the red dots here are the ones that are very impressive because it's bringing together multiple of the techniques together, which is really useful for the determination of the ITRF. And if you talk to someone like Zahir, who has to bring all this information together, what he's looking for is to try and get more of these sites, these super sites, where we've got multiple techniques, because it allows us to remove some of the biases and distortions of the different techniques because they're co-located. So a real benefit of having these together is that we can improve the accuracy of the reference frame over time. And here's something you can just reflect on later on. It shows you the relative importance of the different techniques and what they can be used for. So you can see that VLBI is critical for things like the timing, the rotation rate of the Earth, as I mentioned. That's that UT1 observation there. It's the difference between sun time and Earth time that you would detect with a atomic clock. And you can see that it's the only technique that can do that. GNSS, DORIS, SLR, and lunar laser ranging can't do that. So we need these different techniques because they are complementary. This is just a nice diagram for you to have if you're trying to explain the differences, particularly to decision makers, to say why you need one technique or why you need multiple techniques and not just one technique. And there's a bit more further reading there on things like the ITRF and the ICRF, which is the celestial reference frame, which is made up of our quasars and how that changes over time. So I'll stop there, and good timing, or 1 minute before lunch.